Thank you, Krista, and thanks everybody for being here. So first, I just want to say thank you, John, and of course Keith, for putting together this wonderful workshop. I really enjoyed all the presentations so far. I also like the format that we got an hour to walk everybody through the details. My original plan, of course, was talking about giant planetary dynamics, recent progress, and open questions. But sitting through the talk, actually, Rafa and Paula essentially has tell you guys about it already, right? So what I'm going to do is I'm going to do a graphic summary of the whole thing. Then I'm just going to talk about whatever I want to talk about, right? You guys ready? So here's a graphic summary of giant planet interior dynamics, recent progress, and open questions. So you see, a theoretician is talking to an experimentalist or an observer. He says, very impressive colleague, but does it also work in theory? I think it pretty much summarizes the situation. That is, we have these wonderful observations, but to a large extent, we only have kinematic explanations to them, and we really don't know how dynamically they work out. We're at a fluid dynamics workshop, not at a planetary science conference. So also the correct way to start your actual talk is start with a non-dimensional parameter. So the non-dimensional parameter I'm going to start with is this thing called Q. It doesn't even have a name, right? It's simply known as Q. So what is Q? Q is omega squared A cubed divided by Gm, right? I think everybody knows what omega and Gm is. Omega is the rotation rate, G is the gravitational constant, M is the mass of the planet, and the only thing that needs an explanation is A, right? That's the equatorial radius of a planet. Now, what does that mean, right? Non-dimensional numbers usually are ratios of two things, right? It has a very simple physical meaning. It's the ratio of centrifugal acceleration at the equator to the gravitational acceleration, right? You evaluate that quantity right at the equator. You can easily do the math, and showing this quantity Q describes that, right? So you can measure the Q of all the planets in the solar system, and here they are. Now, if you now start to look at the Q of each of the planets, and you realize that so all the planets in the solar system, when you view them in the lens of Q, they really divided into 3 or 4 different groups, right? You got giant planets, Jupiter and Saturn. They have very large Qs. Their Q is order 0.1, right? Jupiter is about 0.09, and Saturn is actually 0.15, pretty large. Now you go to Uranus and Neptune. They have about order of magnitude weaker, more like factor of 3 to 5 weaker, Q. You go to Earth and Mars, and they're about a few times 10 to the minus 3. So that's the ratio of centrifugal acceleration to gravitational acceleration. Then you go to really slow rotators like Mercury and Venus. They have Qs like 10 to the minus 7, 10 to the minus 8. So they're absolutely tiny. So in this sense, right, giant planets are quite different from terrestrial planets. That you could argue that they are rapid rotators. They are strongly constrained by rotation. Now, we have this rotation, right? This is just solid body rotation. What happens is that, of course, this rotation will distort a planet into a spheroid. Right? You would originally have if you only have gravity, you'd have a spherically symmetric planet. They're just spherical. But if you add a rotation to it and you distort them into a spheroid, you can write your hydrostatic equilibrium equation. Now you have to consider not only the gravitational potential, but they end up having a centrifugal potential that describes the effects of rotation, right? So the centrifugal potential, unlike the gravitational potential, only depends on the cylindrical radius. S, that's distance from the spin axis. You can also write it as an integral, and we're going to come back to that integral because when we talk about differential rotation. All right, so what you do is, then since you can describe both the gravity and the centrifugal acceleration using potentials, you combine the two potentials and call them an effective potential, and this is your hydrostatic equilibrium equation, right? It's grad P equals to minus rho G, and the G is now has both a gravitational contribution and a rotational contribution. We have non-spherical planet, right? Because of the background rotation, you have non-spherical gravitational field. So Rafa mentioned, right? The If you just look at the gravitational field on the surface, you can decompose them into spherical harmonics. And if you get a purely spherically symmetric planet, all the j's would be 0, right? But because you got a rotation, distort them into non-spherical shape, you start to have these all non-zero j's. The j's are also connected to the density distribution inside a planet. But be careful here, right? Although it depends on the density integration along the radial direction, but everything is projected onto spherical harmonics, right? It's the density integration, but then you have to project them onto each of the spherical harmonic degree. So you usually end up getting a very small value, by the way. Now you can do a theoretical calculation, right? If I got a Jupiter-like planet, in this case, a polytrope, and you can calculate the j's, right? You just spin it using a solid body rotation, and you can calculate j's associated with this theoretical planets. And this is actually what I did here. So I'm going to show you a lot of these j plot. So this on a log scale, the jn's, and the field symbol just means that the value is positive, and the hollow symbol means the value is negative. All right, so that's going to be the convention we're going to use for all. And also just to emphasize that j's themselves are actually non-dimensional as well. They are simply an estimation of the gravitational perturbation compared to the background gravity, right? If I say I have a j of 10 to the minus 2, means the degree 2 perturbation of the gravity is 1% of the background gravity. That's what it means, right? So on and so forth. Yes, Nick?
Are these all j's?
Yeah, these are only even j's. When you have a solid body rotation, you would only have even j's because everything is equatorially symmetric.
So what is the other dimension?
Yeah, I mean, there essentially is a mapping of, essentially it comes from the mapping of the centrifugal potential, which is dependent on S, onto spherical harmonics. It's almost like a Gibbs phenomenon that you need to have lots of cancellation to end up having that. Yeah.
Hal?
Yes.
Does this calculation take into account the change in the density distribution because of the rotation?
Yes. So this is a full calculation. I'm going to show you a little bit more detail on that. All right. So what's been done here is using something called a polytrope of index unity. So this is assuming that pressure and the density has a connection like this. And it's not only a polytrope of index unity, not only is a good representation of what Jupiter's internal density is like, but it also has very nice analytical properties that will allow you to construct solutions exactly. So here's the internal density profile corresponding to this theoretical planet. And you can see there are two different density profiles. One is along the equator, one is along the pole, because the planet is now non-spherical, right? So if you have this equation of state, you can show that it admits a very simple general solution that's essentially spherical Bessel functions and Legendre polynomials, right? Once you have that, you know the density everywhere at every location inside this planet. You know the shape of this planet everywhere, and you can compute your j's, which is the integration I showed you earlier, right? Now you would also notice, right, if you have solid body rotation, not only do you have alternating signs, as Nick pointed out, it's also a parallel decay, because you can also show that the j, or the even j's, is actually proportional to the smallest parameter I introduced, q. So j to n is proportional to q to the power of n, right? There's additional terms here. It's actually q to the power of n and n plus 1 and plus 2 and all that. So what does that mean, right? At Jupiter, we can measure its gravity to about 1 part in a billion. So that's the accuracy of the measurements. And you got a q of 0.1. That means if you're going to do a Tyler expansion or to get an accurate enough q, you're going to have to Tyler expand to about order 8 or order 9, right? That's the challenge. However, if you're doing this at a terrestrial planet, where q is 10 to the minus 3, you do a third order theory of figures, you're done. Right? So that's why, theoretically, even just computing the static j's is a huge challenge because q is so large for giant planets. Now, from our solution, we can also construct, right, this part of the solution That is also the internal shape of this planet. So what's shown here is the so-called effective ellipticity. This is just to describe how elliptical your planet is, and the ellipticity is different, right? So if you got a sphere, you got an ellipticity of 0, right? C equals to A. If you got a line, you got an ellipticity of 1. So that's the range. You can see, right, from the surface to the center of these theoretical planets, the ellipticity is decreasing, meaning the planet is actually getting more and more spherical as you go inside, right? You measure the shape at the surface of the planet. That's a measurable thing. But you don't know the shape at each of the layers inside because it's not the same. As you move from the outside to inside, the shape of the planet changes, right? So that's what Bill Hubbard did in 2013. It's called concentric Maclaurin-Freud method, and that's essentially the theoretical breakthrough you needed to even forward compute the theoretical J's for giant planets, because third order theory of figures only gets an accuracy about 10 to the minus 3 for the giant planets, and the measurement goes up to 10 to the minus 9. So the theory, this is like the theory of figures, but the concentric Maclaurin-Freud is you construct different Freud for each layers. All right. I've also mentioned, actually, we have measured the shape of Jupiter, of course. This is the value we have measured, right? You take the 1 bar surface, you know the equatorial radius of Jupiter, you know the polar radius of Jupiter. It has an effective ellipticity about 0.355. So this is also more or less consistent with our theoretical values, right? This is a simplified theoretical model to illustrate the principle of this is not to match Jupiter. Right? Now, how about differential rotation, right? So everything I've talked about so far is you've got solid body rotation, right? That gives you all these J's, and these J's would follow a particular pattern. Now, how about differential rotation? Let's say, you got a planet, right, Jupiter, that has differential rotation. You will see them on the surface. Now, what happens if part of this differential rotation also penetrate through, say they are extended through the inside of a planet? Right? Let's say this part, let's just say this part of the planet, the equatorial region in the cylinder, is rotating faster than the rest of the planet. What's going to happen to this part? You're going to have a higher centrifugal, experiencing slightly higher centrifugal acceleration. We want to further bulge out. Right? That's actually exactly what happened. If you then compute the response of if you just add an equatorial superrotation, so the equator will start to bulge out, and the poles would actually shrink. Right? There are different ways of understanding, because this whole thing, once you start to change the shape here, you change the density perturbation, and that has feedback effects on everything else. I mean, the density is non-local, right? Gravity field is non-local. You change density at one place, you change the whole distribution, right? Another way of thinking about it is like the whole planet would become more oblate, because if you think about the total angular momentum of these planets, because of the superrotation, the total angular momentum of this case is higher than the previous case. So the whole planet would become more oblate. If the differential rotation is entirely on cylinders, it turns out that you can still solve the whole equation using potential theory, because it turns out you can simply change your centrifugal potential to include the differential rotation term. Right? This is only true if the differential rotation is on cylinders. Right? This is like a coincidence with Taylor's constraints. But I don't think the two are directly connected in any way. But I sometimes wonder, is there a deep meaning behind the two? That is, if you got rotation that are constant on cylinders, that will allow you to write this whole equation in a potential form, because then you still can define a centrifugal potential, but now take into account of the differential rotation, right? So we can still solve this whole equation like that, and that's all. You don't have to do anything fancier than that.
Sorry,
yeah.
When do you stop integrating? Because you have to integrate from the inside.
Yes.
And what's the boundary condition?
Yeah, the boundary condition for the polytrope, great question, yes. Let me go back to the... So in this particular case, another nice thing about the polytrope is that the boundary is where density goes to 0, all right? And you know that it's essentially that's the first 0 of the spherical Bessel functions. So that's right. In reality, at giant planet, we tend to stop the integration at 1 bar level. We can also do that here, but it's a choice. Right? You choose to stop your planet. I mean, in this case, we can stop it at 0, but you can also say, I'm choose to stop my planet where the density hit 0.1. So that's all doable. All right. Okay, so with that, right, if I got a cylindrical differential rotation, I can still solve the equation entirely analytically. Well, you have analytical form. What you do is you find the coefficient of the spherical Bessel functions. Okay, so this is what happens when you do that. Right? So the black dots are when you have no differential rotation, just a solid body rotation. So you got a power law decay of the J's. So the 3 colored lines is when you have at a cylindrical differential rotation just at the equator. If you notice, if you look closer, right, the 3 different colors just means the cylindrical winds, I have a next plot, means the cylindrical winds has a slightly different depth, right? So that's all. The shallowest to deepest, right? You may say, well, why do you have these oscillations? Because for the solution to converge, I need to use a truncated series to represent the wind so that the solution actually converges, right? But you might notice, right, I got 3 different winds. One is 0.975 deep, the other is 0.9 deep, there's 0.8 deep. Their gravitational perturbations are the same. If you look at the high degree J's, J12 and above, they're pretty much on top of each other, right? So why is that the case? It turns out the high degree JNs actually saturate if your wind goes too deep. If you look at the wind-induced JNs, at the low spherical harmonic degrees, they're still quite different. Right? The deeper wind induces a stronger delta J2, right? And delta J4 and delta J6 or so on. But once you go to about degree 10 or so, everything becomes roughly the same. They all saturate, right? And there's 2 effects here. One is the definition of Jn, that you got an integration factor of r to the power of n. Right? As you go to higher and higher n, you're only sensitive to the outer layers. All right? So keep that in mind. Right? So if you only measure the high degree Jn's, you try to figure out how deep the wind is, you might run into a saturation problem that is the signal from the deep winds saturate at these higher Jn's, right? Okay. But these calculations you can do with, cylindrical winds, right? Once you have cylindrical winds, you can write centrifugal potential, you can do it, you can solve it, right? But the winds on Jupiter are not on cylinders. Well, they have to stop somewhere. So how do you do that, right? So this has come from the, where the quote-unquote thermal wind equation comes in. I must confess, right, this is an inappropriate name. If I have a choice, I would call it a thermal wind-like equation, because it is not the thermal wind equation we use for dynamics in Boussinesq approximations and inelastic approximations, right? So what you can do here is, you say, I got winds, and the winds are small compared to the background rotation. So I'm going to decompose my wind into a background rotation and a differential rotation. I'm going to decompose my density and my pressure into these terms as well. Then you just expand out your Euler equation, right? And most of these terms looks familiar to you, but you got some additional terms, particular for the gravitational problem, as I alluded to earlier. Once you change density one places, you start to change the gravity field elsewhere as well, right? Now, if you want to be ignorant, say, I'm just going to keep the quote-unquote leading order terms and take the curl of this equation, and this is what you get. I mean, it looks quite like the thermal wind equation, but if you look closer, right, what you're doing is you're doing the derivative of the momentum, not the velocity, as a function of z, right? And that gives you a density perturbation gradient, and that density perturbation has both a thermal contribution and a pressure contribution, all right? So in the cylindrical wind problem, there's no thermal perturbation. Right? The wind is constant along cylinders. Thermal perturbation is zero everywhere. You have pressure difference along these fronts. And this pressure difference gives rise to the density perturbation. Right? In that case, you can even have two different understanding of the wind, right? You can say locally it's the density changed. You can also say it's really where my isobaric surfaces has distorted, right? But nonetheless, they give you, gravity variations. So this is what you do, right? For this, cylindrical case, I can compute what the exact solution is, right? Taking into account all the terms. I can also just do a simplified calculation, integrate this thermal wind equation. I can also get my gravitational perturbations. And if I plotted them all together, this is what they look like. So they pretty much agree with each other on this level. They agree with each other to about 10% level. Okay. If you look at the exact details, they can't deviate from each other. But this much simpler equation do captures order of magnitude, not only order of magnitude, I would argue. So that gives you a tool to forward calculate the gravity field associated with any wind profile, and that would allow you to using that as your forward model to yes,
yeah. Is there a reason why J24 always seems to vary a bit more compared to the rest?
Well, good question. Let me think about it. Yeah, I think at this point that this is where remember that when I say, when I construct the wind profile, I have to truncate the wind profile so that the solution converges. And this is pretty much where the wind profile got truncated. So I think after that, this is a different effect. Yeah. Okay. All right. So hope that's a premiere on how the data analysis works and what is the theoretical foundation of all the data analysis. So let's now go to the data. Right. What the Juno mission has given us is measurements of Jupiter's gravitational field and magnetic field and many other things. And I'm only going to talk about the gravitational field and the magnetic field. It is still ongoing. It arrived there in 2016, and the extended mission is supposed to end this year, and we just submitted the extended mission proposal end of last year, and we're waiting to hear back from NASA. Here's the set of instrument on board Juno, and there's also a human for scale here, telling you the size of the spacecraft. The Juno spacecraft is the first solar-powered spacecraft that traveled beyond the asteroid belt. The solar panels are big. Each of the solar panels is about the size of a school bus. So you see this big dish called gravity science. And the gravity science, or the measurement, is really just the radio waves, right? Just the communication signals, and you're just measuring the Doppler, right? As Juno orbit Jupiter, you're using the Doppler to measure its velocity, and then from the velocity and the trajectory, you back up the acceleration. So now, before I show you Juno data, I want to show the zonal winds on the surface of Jupiter. This has been shown many times. We got a question? Nick.
I was just curious, proposals for extended missions aside, how long can this thing hang out up there before there's a problem?
So far, everything is healthy, and the radiation dosage is smaller than we expected. One of the danger we have to worry about is as the orbit precesses, what happens is that we'll start to run into the rings of Jupiter in the equatorial region. And arguably one of the biggest dangers is that there is a large particle in the tenuous ring of Jupiter, and we just hit it.
Okay.
Yeah. But we think it's tenuous enough, the chance is small enough, we'll just go ahead and do that. Yes. Great. Yeah, because it's solar powered and the solar panels are not degrading that much, so we don't have a power issue. Yeah. And the radiation is benigner than we expected. Yeah. All right. So what I'm doing here, on the leftmost plot, I'm showing you the measured zonal wind velocity on the surface of Jupiter in the rotating frame, showing you u phi. Now here's in the same spirit as showing the angular velocity, right? If you show the angular velocity associated with these winds and take the ratio to the background rotation, and this is what the profile looks like. And I want to point out, right, this is about 10 to the minus 2, or 1%, right? The differential rotation on the surface of Jupiter is about 1% of the background rotation, right? This is quite different compared to the solar convective zone, right? In the solar convective zone, the differential rotation is 30% of the background solar rotation. Here we're talking about a 1% deviation, right? Is it a strong wind? Is it a weak wind? Depending on who you're talking to. But order of magnitudely, we're looking at a 1% superrotation or subrotation, right? That's what we're talking about. Now, when we analyze gravity, right, we decompose them into spherical harmonics. You can do the same thing for the wind, right? I measured the wind. I can decompose its angular velocity onto a set of spherical harmonics, the same set of spherical harmonics I use to express my gravity. And if you do that, this is what you get. Again, this is non-dimensional, right? This is the ratio of the angular velocities. And this is the spectrum, quote unquote, spectrum you get when you look at, when you decompose the observed surface winds onto a set of spherical harmonics. And you will notice the power peak is at about degree 24 and degree 25. Right? That's the characteristic wavelength if you do a spectral analysis. So what does the data look like, right? So here's the data. Sorry, it's a bit of a busy plot, so let me walk you through it slowly. You see this set of red dots. Right? If that reminds you anything, right, that's the theoretical calculation, what the J-ends of a solid body rotating of Jupiter look like. This is not a theoretical calculation using a simple polytrope anymore. This is a theoretical calculation done by Burkhardt and Militzer using an actual equational state of hydrogen and helium and add a bit of heavy elements in it. But this is, again, the general behavior is the same. They would decay to the power of q to the n. Right? You see a set of black dots and blue dots. These are the measured J-ends. Right? So initially, you see they basically follow what you expect from the solid body rotation. From degree 10-ish, you start to see the level off. Right? You start to level off. And you also see these so-called odd modes, which is the north-south asymmetric gravity field. And if you look at the winds, of course, there's a big north-south asymmetric component of the wind. Right? I mentioned earlier, J-ends are non-dimensional. Right? They're really just telling you the perturbation to the gravitational field. So how big is this level off? Or how big is this dynamics-induced gravity? 10 to the minus 7, right? 1 part in 10 million. So all these zonal winds we're seeing, right, 1% of zonal winds, induces a change to Jupiter's background gravity field about 1 part in 10 million. That's how big it is. Right? That's how small it is, but nonetheless we can measure it. And you also see the derived uncertainty and twice the derived uncertainty. And the claim we made that we can measure Jupiter's gravity field to 1 part in a billion comes from here, of course, in a low-degree spherical harmonics. Okay? All right. So if you just differentiate, right, between the measured data point, you can't even see that very well. It's the black dots. And then the red is what you expect from the solid body rotating Jupiter. I mean, the exact model doesn't matter even that much, right? Because it's a q to the power of n decay, so it doesn't really matter that much. And of course, all the blues dots are supposed to be, dynamics induced, and most likely they're wind induced. So what you can do is you say, well, just like I construct the gravity field, I can forward construct any wind I want, right? Then I can compute the gravitational harmonics associated with that wind. I can do the same thing, right? So I just do a bunch of what we call it, single wind mode, right? For example, this is just a kinematic profile. This is a degree 20 spherical harmonics. Then I just project them along the z-axis. Then I truncate them at a particular depth, right? I gave this wind to my interior density profile, then I can calculate the JNs associated with set of winds, right? I can calculate JNs with this set of winds. We used a relatively sharp decay profile, right? That's guided by the work of Uli Christensen, and Paula also mentioned that. And we're actually going to vary the depths, in our experiment. But once you do that, you can start to write the whole problem in a linearized fashion, right? You can actually put them into a matrix format, right? You got a forward model, which is our thermal wind balance, which is not the full Euler solution because the winds get truncated, right? You're going to describe your wind, deep wind, just by the set of coefficient. You're going to assign it to them. Then you're going to try to say what type of combinations of wind are going to give me these gravity harmonics, JNs I'm going to measure, right? Everything is known except these deep winds, right? You throw this to the machine, this is what you get, right? Again, blue is the observed wind on the surface of Jupiter. Red is what you get if you construct it from gravity, right? I want to emphasize, right? In doing this construction, the red line knows nothing about the blue line, right? The only input I gave to get the red line is the measured J's and the background density of Jupiter. That's it, right? You gave the background density of Jupiter, which gives you the left-hand side, and then you give the measured J's, you do an inversion, and this is the red line. The red line knows absolutely nothing about the blue line, doesn't know anything about the surface winds, doesn't know any wind at all. And we pretty much fall on top of each other in most of the places of interest, which I find quite interesting, right? This is assuming a depth of 2,500 kilometers, right? You truncate the wind at 20, yeah, Ben.
The red line also, you've built in your truncation depth. That goes into that red line.
That's right. So I'm going to show you different lines with different truncation depths, right? So the red line is a line you get when you say the truncation depth is at 2,500 kilometers. Exactly.
There was a calculation of barotropic stability criterion by Ingersoll many years ago.
Yeah.
For the old profile. If you computed for this profile, how do they compare?
Yes, that we haven't done, but I mean, as I said, right now, this is kinematic calculation. We have not gone and do, say, a dynamical evaluation of the stability of these wind profiles, but that's something we can do, of course. But yes, that's actually something on the radar. But this is what you get, right? So if you take a closer look, you may say, well, you got a deviation from the measured surface winds right at the equatorial region. Now, you can also evaluate, right, because the gravity solution has uncertainties associated with them, right? You can also evaluate the uncertainties associated with our inversion. You would immediately notice two things. One is the uncertainty is very large in the southern hemisphere. We almost cannot say anything about the winds in the southern hemisphere. Why is that? Why is that, right?
Why is the actually for if you have all the even mode, even J2, J4, or J6, why do you get the asymmetrical profile in the speed?
Well, we have odd J's as well.
You have also have J1.
Yes, we have no J1, start with J3. J1 is just the center of mass location. Right.
I remember the precession orbit you showed before, it only probed the northern hemisphere.
Yeah, so that's actually the reason why we have terrible, not terrible, but depending on, we have worse precisions in the southern hemisphere compared to the northern hemisphere, right? As the Juno orbit precess, when we come in, it's pretty much north-south symmetric. But as the orbit precess, that we're getting closer and closer to the northern hemisphere, but we're also moving further and further away from the southern hemisphere. So, our understanding of the gravity field of Jupiter is much better in the northern hemisphere compared to the southern hemisphere. And that's also why, when we do the formal aero analysis, we end up having a much larger uncertainty in the southern. We also have larger uncertainty in the equatorial region, and that's what's being discussed already. That is, we simply have weak sensitivity in the equatorial region, and that's a geometrical effect, right? It's a sphere. When you project a sphere along cylinders in the equatorial region, there's very little mass, and d rho dz goes to 0 at the equator. So you got sort of two penalties acting on you at the same time, so you end up having work. But in the mid-latitude, in the northern hemisphere, we are pretty sure that what we see on the surface, these off-equatorial jets are fairly deep, right? A few thousand kilometers deep. So that's one depth, right? What happens if you actually vary these depths? And this is the series of lines you get, right? If you go to shallower depth, say 1,500 kilometers, you would have stronger winds. The equatorial jet increased by about a factor of 2. I think let's focus on this part. You know that this part where we have good sensitivity. Don't pay too much attention at the equator and at the southern latitude, because you know that we have worse sensitivity there. So if the winds, deep winds, are twice as strong as the surface winds, they might be only 1,500 kilometers deep. So that's starting to move away from the MHD region, meaning the truncation of the winds or the stable stratification may be some deep radiative layer, right? So we started talking about implications. The other thing you might notice, right, which I alluded to earlier, if you try to get a wind which is 3,000 kilometers deep, you get pretty much the same thing when you try to get a wind that is 2,500 kilometers deep. That is, gravity starts to lose sensitivity if you put the winds too deep. So in a sense, the gravity solution cannot tell you how deep the wind actually goes, in a sense, right? It tells you it probably has to go at least 1,500 kilometers if you want a reasonable depth, right? So this is just a review of what the Galileo probe result was. So Galileo probe was dropped into Jupiter at an equatorial region, and as it moves into Jupiter, this is what the derived wind speed. This is on pressure coordinates from 1 bar to about 20 bar. So you can see between about 1 bar and 5 bar, the equatorial wind actually increased by a factor of 2. Right? You go from 90 meters per second to about 180 meters per second. And after that, it stayed constant. Right? Everybody has been ignoring this. Almost everybody has been ignoring this because they don't really show up in simulations. Right? But this is the single point measurement we have, and the wind increased by a factor of 2. Right? If that's the case everywhere, well, I don't know if that's, but if that's the case everywhere, my solution would argue, right, the winds probably are not that deep. They could be as shallow as 1,500 kilometers. Right? Still fairly deep compared to the wind, compared to the weather layer, but they're not that deep. May not be that deep. So here I'll come to the big unknown.
Sorry, if you go even shallower, what happens? Why have you stopped at 50?
You start to have too strong a wind.
Okay. It just takes off.
Yeah, that's right. Yeah. And I think Boris mentioned this, right? We haven't really done, dynamical stability analysis, right? A lot of the solutions may not even be dynamically stable, yes. But yes, they actually start to go exponentially higher, the wind velocity, because as you go shallower and shallower, the density drops so fast. Yeah. So, all right. How am I doing on time? I'm supposed to wrap up in 10 minutes? 12:20. Okay, 10 minutes. All right, so I have a little bit of time to talk about magnetic fields. So we're talking about the deep atmosphere of Jupiter. We have lots of question marks. For example, in this interesting region of 600 to 1,200 kilometers, are there rock clouds? Are there deep radiative zones? Right? In a deeper interior, actually, we know there's a dynamo. And we more or less know the wind probably is no deeper than about 2,500 kilometers because of the ohmic dissipation constraints, by the way. You don't need gravity to tell you that. Right? So if you've measured the heat flux out of the planet on the surface, you know how strong the magnetic field is, you know how strong the electrical conductivity is, you can actually kinematically calculate how strong the wind can be at each depth if the ohmic dissipation does not exceed the surface heat flux. And this is in calculation for Jupiter and Saturn I did. This is 100 meters per second, right? I measure the surface winds. This is 0.1. This is 1 centimeter per second. Where the kinematic limit applies is pretty much where the depths, sort of inferred depths of the wind. I think Paula mentioned this already. Probably not a coincidence, but no one can sure.
What's TD and T naught?
T0 is the temperature at the surface of the planet. TD is the temperature at where the dissipation happens. So in the stratified system, the dissipation can actually be stronger than the surface heat flux, but it's still bound by a limit. I think Mike has a question.
Yeah, could you repeat, how do you do that? How do you make that come?
You project the wind along cylinders to the interior. Then you do a kinematic calculation because Rm is small. And if you do a kinematic calculation, you can solve the induction equation to get the J, then can calculate the ohmic dissipation by integrating J squared over sigma. Yeah, so it's a kinematic calculation.
But you're just assuming that dissipation arises primarily from the zonal flow.
Yes. This is assuming what is kinematically calculating the dissipation associated with deep zonal flows. That's exactly what I did. And from that, you can get a limit on the wind speed. Right? You know the wind deep inside Jupiter cannot be even meters per second because otherwise there would be too much dissipation.
Sorry, and is it sensitive to your kind of tangent function at the bottom? Does it care on your gradient?
Very good question. So in order to do this kinematic calculation, what you have to do is you assume the wind decays faster than the conductivity decays. So you give it a sharp decay that has a smaller scale height compared to the conductivity scale height, because otherwise your J is still increasing as you go inside. Right? Again, right, this is kinematic calculation. Because if that's not the case, then you'd run into even higher dissipation. In terms of getting a limit, I think that's the right thing to do. Okay, so I have 5 minutes on magnetic field, so what should I cover? So let me quickly, 8, okay, even less than I expected. So I'm just going to quickly flash, right? We do know, right, the 4 giant planets have a magnetic field. Jupiter has a really strong magnetic field, and we also have measured, confidently measured, their internal heat flux, except for the case of Uranus, and they also have quite healthy amount of cooling. Let's see. Now, if you just look visually, you're saying, well, Uranus and Neptune seems to have a very different magnetic field compared to that of Jupiter and Saturn. You can also do this in a slightly more quantitative fashion, is to calculate something called the dipolarity, which is just the ratio of energy in the axial dipole to the ratio of the total magnetic energy being measured. You can evaluate this at the surface of a planet. You can also evaluate them inside the planet, assuming that region you evaluate them has no electrical currents. If you just do so, you would say Earth, Jupiter, and Saturn all have a dipolarity greater than about 0.1. And if you do so for Uranus and Neptune, and they have a dipolarity less than 0.1. And the big question is why that is the case. Right? Not going to answer that question. I don't even think we know the answer to that question. So plug in. Krista, Mike, and I recently worked on the annual review article, and we just received the proof this morning. Apparently, we even have a DOI on it, but it may come up at any moment, right? We were told. All right. I do want to maybe use the last 5 minutes or so talking about these particular aspects of the magnetic field of Jupiter, right? So not only Juno has measured the static magnetic field of Jupiter, which gives you a map like this, got a flux band in the northern hemisphere, mid-latitude region, got a magnetic spot, one spot near the equatorial region, which we decided to call Great Blue Spot, just because we're using a blue-red color bar. And then the southern hemisphere looks more or less like that of a dipole, right? So not only we have measured this, and we have also used Juno measurements to figure out the deep wind profile inside the dynamo region. That's doing secular variation, right? You track the changes in the magnetic field using that to figure out the drift velocity. And this is the profile we get. It features, again, a single equatorial jet, but pretty broad, like a lot of dynamo simulations, right? And the amplitude of this equatorial jet is less than about a centimeter per second. So we do have a dynamical constraint on how fast zonal flows are in the dynamo region of Jupiter, which is about centimeter a second. Right? We also know the boundary on the surface is 100 meters per second, but the convective velocity is still unknown. Right? We have not, let me be slightly careful, right? The data does not require any non-zonal flows. Right? In order to explain the secular variation data in Juno orbits, you can explain all of them with just the zonal flows, and that's what we derived. And there's no requirement to have any vortices or anything like that. So right now, observationally, we do not know the convective velocity. Right? In a lot of dynamo simulations, right, this is really extrapolation, convective velocity and zonal velocity can be similar. Right? In the dynamo region with strong magnetic field, the two can be very similar to each other. And even if the convective velocity are weak compared to that, usually it's not that weak. So maybe it's not too bad. 5 minutes, okay? Or 3 minutes. So in addition to having a static or steady state, deep zonal flow, we have also looked at the few orbits that target the so-called great blue spot. Because great blue spot has very strong magnetic field gradient around it. If it moves, it would induce more magnetic field signals compared to other regions. So if you want to look at changes in magnetic field as a function of time due to motions, this is the best place to look. Right? So Juno has these dedicated orbits that flew by great blue. Some of them are just accidental. Right? Some of them, actually, we asked the Juno operation team to give us a flyby around the great blue spot. I think 3 or 4 of them are like targeted great blue spot flybys.
Does it coincide with the great red spot?
It's arbitrary. The color is arbitrary, right? It's not coincided with the great red spot because great red spot drift. And this thing is basically static within the rotation. It has a small zonal velocity, which is less than a centimeter a second, right, compared to the background rotation. Right? Great blue spot themselves drift a lot faster. Yeah. So, all right. So if you look at these targeted flybys around this great blue spot, and what we think we've seen is that there seems to be a 4-year oscillation around it. Right? If you look at the magnetic field associated with the great blue spots and just apply the same background steady state zonal flow profile there, but now allow additional degree of freedom in how it changes with time. And the data do seem to suggest there's a 4-year oscillation around this background. This is highly tentative, I should say. Right? I mean, we only have observation of 4 years, right? You don't really know what the period. But I think we can confidently say this thing seems to be changing, right? I think I'm on time. I don't think I have time to talk about Saturn, so I think I'm going to stop here and just summarize with this figure. Yeah, I think we have collected amazing observations in the case of both Jupiter and Saturn, gravity and magnetic field, but dynamically we don't really understand how this system works. Okay, thank you.